If the idea that two monster storms could lock together over the American heartland and shatter every forecasting model NOAA has you as unsettled as it has me, make sure to hit like and subscribe to Signal Watch so you don't miss a single update as this story develops. Drop a comment below. Where are you watching from? What's your local weather right now? And do you trust the 7-day forecast on your phone? Or has it let you down when it mattered most? If you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Now, before we get into it, here's what this investigation is going to cover. A Japanese meteorologist described the mechanics of this in 1921, and every computer model built since then still struggles to predict what happens next. In 2009, a Fujiwara interaction over the Philippines turned a weakening storm into an unforecastable killer that made 3 separate landfalls and left nearly 500 people dead. And that was over ocean, not over land. The 1993 Great Flood of the American Midwest was driven by a single stalled atmospheric pattern, not 2 locked storm systems, and it still put 600 river gauges above flood stage simultaneously and caused $15 billion in damage. And there are levees along the Missouri and Platte rivers right now that the Army Corps of Engineers has publicly stated remain vulnerable. And a stalled superstorm doesn't stop when the levee fails. It keeps raining. Now, settle in. Let's get into it. 2 low-pressure systems are moving across the central United States. On paper, they're being tracked as separate events. Each one has its own advisory chain. Each one is generating its own model runs. Your local meteorologist is probably talking about one of them, maybe both, as individual weather systems that will move through your area in the next several days, bring some rain, kick up some wind, and track northeast toward the Great Lakes the way storms in this part of the country are supposed to. Here's what that framing misses. These 2 systems are inside a threshold that most people have never heard of: extratropical cyclones, the large mid-latitude low-pressure systems that produce the most significant non-tropical weather in the continental United States, begin binary interaction when they close within 2,000 kilometers of each other. At 1,100 kilometers, the acceleration phase begins. Their circulations start to feel each other. They begin to influence each other's tracks. And if they continue closing, something happens that the most powerful weather forecasting computers on Earth still cannot reliably predict past a 48-hour window. They lock. The technical term is binary cyclone interaction. The phenomenon is named after a Japanese meteorologist who first documented it in 1921. And when it happens between 2 systems of roughly equal strength, which is the case developing right now, the outcome is, in the precise language of the research literature, extremely difficult, if not impossible, to forecast by numerical weather prediction models. That's not a dramatic characterization. That's a direct quote from a peer-reviewed paper published in 2020 analyzing the most documented Fujiwara interaction event in modern meteorological history. Right now, the Global Forecast System, the GFS, the primary operational model run by NOAA 4 times every day, the model that powers most of the weather apps on your phone, is showing dramatically different track solutions for these 2 systems across its ensemble runs. That spread, that divergence, is not noise. It's a signal. It's the model telling you, in the only language it knows, that it doesn't know what happens next. This is the central problem this investigation is going to examine. Not just what a Fujiwara merger does to rainfall totals or wind speeds. Those numbers are alarming enough, and we'll get to them. But what it means when the system we trust to tell us where the storm is going is the first casualty of the storm's arrival. Because what the National Weather Service's operational models are built to do, extraordinarily well, in most circumstances, is track individual storm systems. They solve the dynamical equations of atmospheric flow for a single low-pressure center. They ingest observational data from radio sondes and weather satellites and ground stations and produce forecasts that, for a single system, are now skillful, out to approximately 2 weeks for large-scale patterns. But Fujiwara interaction is not a single system. It's a coupled system. 2 vortices orbiting a common center, each one influencing the other's intensity, and track in ways that are exquisitely sensitive to the initial size ratio, the initial strength ratio, and the initial separation distance between them. Small errors in measuring any of those three variables compound rapidly during the interaction phase. By 48 hours into an active binary interaction, the range of possible outcomes spans the difference between a fast-moving storm that tracks northeast and clears the region in 36 hours versus a stalled, merged supersystem that parks over the Missouri River Basin and doesn't move for 5 days. The models are producing both of those solutions right now, simultaneously, with comparable probability weights on each. That is what forecasters mean when they say they're terrified, not hyperbole. Not headline writing, an honest description of the state of operational meteorological science when confronted with a co-equal binary interaction over flat continental terrain with no geographic forcing to resolve the ambiguity. And to understand why the resolution matters so much, why the difference between those two model solutions is the difference between a manageable event and a generational catastrophe, you need to understand something that a Japanese scientist figured out with nothing more than a tank of water and a century's head start on the rest of us. Sakuhei Fujiwhara didn't have satellites. He didn't have computers. He didn't have a supercomputer running 4 ensemble members every 6 hours and comparing them against European center model output. What he had was a rotating tank of water, a methodical mind, and the patience to watch what happened when two vortices of equal size were introduced near each other in that tank. What he observed every time was the same. The vortices didn't continue on their independent paths. They didn't simply push against each other and bounce apart. They began to orbit, slowly at first, circling a common center point between them, drawn together by the mutual influence of their circulations. And if left undisturbed, if no external force intervened to break the symmetry, they spiraled inward. They merged. Fujiwara published his findings in 1921 in a paper titled The Natural Tendency Towards Symmetry of Motion and Its Application as a Principle in Meteorology. The name he gave to the phenomenon was characteristically modest. He was describing what he had seen in a water tank. He could not have known that 105 years later, meteorologists would still be invoking his name when trying to explain why their most sophisticated models failed to predict the deaths of 500 people in the Philippines. The physics Fujiwara documented is not complicated to state, even if it's extraordinarily difficult to model. Two cyclonic vortices in the same fluid, whether that fluid is water in a tank or air in the lower troposphere, exert mutual attraction on each other. They begin orbiting a common center. That center point is not fixed. It migrates toward the stronger vortex if there is a size or intensity difference between the two systems. As they orbit, they draw closer. And the closer they get, the faster they orbit, and the stronger the mutual attraction becomes. At approximately 300 kilometers separation, the merger becomes realized. The two circulations are close enough that they can no longer maintain distinct identities. They combine into a single larger vortex. The phenomenon was popularized in the United States through a 1951 research paper analyzing Pacific typhoon interactions from World War II military weather records. American meteorologists studying why certain typhoon tracks had been so unpredictable enough to delay General Douglas MacArthur's planned occupation of Japan in 1945, when two typhoons interacting within approximately 1,200 kilometers of each other produced hazardous weather that required a 48-hour delay, found Fujiwara's work and recognized it as the mechanism they'd been observing without a name. The first well-known instance documented in the modern era came in 1964 when Typhoon Marie and Typhoon Kathy merged in the Western Pacific. The effect was examined in the Monthly Weather Review Journal in November of 2003. That analysis establishing the factors that govern which of several possible outcomes occurs. And those outcomes matter enormously because they are not equivalent. When two cyclones interact, there are 3 possible results. The first is elastic interaction. The systems deflect each other and separate, going their own ways. Think of 2 magnets repelling. This is the most common outcome when the size or strength difference between the systems is significant. The larger system dominates, the smaller one is flung away. The second outcome is partial merger. One system is absorbed into the other, which becomes stronger and more powerful, but the interaction resolves relatively quickly. The third outcome, the rarest, the most dangerous, and the one most strongly associated with catastrophic damage, is full merger. Two co-equal systems spiraling together into a single amplified vortex that is larger, more powerful, and in many documented cases, effectively stationary. A 2020 research paper published in Science Direct analyzing the most devastating Fujiwara interaction event in the modern record classified 3 distinct interaction types across a single 14-day period: elastic interaction, partial merger, and partial straining out, all occurring in sequence as 2 typhoons danced around each other over the western Pacific. The classification was determined after the fact. The models couldn't determine it before. The reason for that forecasting failure, the specific physics of why binary interaction breaks model skill, comes down to sensitivity. The outcome depends on the precise ratio of size and strength between the 2 systems at the moment of closest approach. If that ratio deviates from 1 to 1 by more than approximately 20%, the stronger system dominates and the interaction resolves. If the ratio is close to 1 to 1, the systems are genuinely co-equal, and full merger becomes the most likely outcome. Measuring that ratio accurately in real time for 2 large extratropical cyclones whose circulations are already beginning to overlap and interfere with each other's observational signals. That is where operational meteorology reaches the edge of what it can reliably do. And the first time most of the world understood what full merger meant in human terms, it wasn't over the central United States. It was over an archipelago in the western Pacific, a system that meteorologists thought was dying, a city they thought was safe, and a storm that came back 3 times. October 2009. The Philippines had already been hit hard that season. Typhoon Ketsana had struck just 8 days earlier, flooding Manila in the worst inundation the city had seen in 40 years, killing nearly 300 people. When Typhoon Parma approached from the Pacific in late September, the country was already exhausted, its emergency systems already stretched. Parma made landfall on the northern tip of Luzon Island as a Category 1 typhoon. By the time it crossed the island and moved into the South China Sea, it had weakened significantly. The models agreed Parma would continue westward, track away from the Philippines, and dissipate. The threat, officials believed, was over. Then from the east came Super Typhoon Melor. Melor was a much stronger system, a full super typhoon with sustained winds well above those of the weakened Parma. When Melor approached from the east, the 2 systems were approximately 1,000 kilometers apart. That is inside the binary interaction threshold for tropical cyclones. Their circulations began to feel each other. What followed was documented in precise technical detail by a research team that published their analysis in Science Direct in 2020. Using differential image processing techniques on satellite composites, the researchers classified what happened over the following days: elastic interaction on October 3rd, 4th, and 8th, partial merger on October 6th, partial straining out on October 7th. Not one type of Fujiwara interaction, all 3, in sequence, across 14 days. Parma, pulled by Melor's circulation, stopped its westward track. Then reversed. It moved southeast, back toward Luzon. Then it made landfall again, then a 3rd time. 3 landfalls. The same island, the same communities that had been recovering from the first impact, then the second, hit again. The researchers' conclusion about what this meant for forecasting was unambiguous. Typhoon Parma's track was, they wrote, extremely difficult, if not impossible, to forecast by numerical weather prediction models. That language, precise, technical, written by people who spend their professional lives building those models, is as close as the research literature gets to saying, we couldn't see this coming. The human cost of that forecasting impossibility, approximately 500 fatalities, $581 million in economic losses, landslides that buried villages, rivers that crested 3 times as Parma crossed and recrossed the same watershed. The San Roque Dam releasing water to prevent its own breach, sending additional flooding downstream into communities that had nowhere left to go. Now, there is something critically important to understand about the Parma-Melor interaction that makes it both the most instructive and the most alarming analogy for what we're watching develop over the central United States. Parma was a tropical system. It was occurring over ocean. And eventually, after 14 days, after 3 landfalls, after 5 days of continuous impact over Luzon, Parma dissipated. The ocean ran out of the warm surface water the storm needed to maintain itself. The interaction with Melor ended. The storm died. That mechanism does not exist over the Central Plains. There is no ocean temperature to cut off. There is no coastline to weaken the circulation against. When a Fujiwara interaction locks 2 extratropical low-pressure systems together over Kansas, over Nebraska, over Iowa, the only thing that ends the interaction is a large-scale atmospheric pattern shift strong enough to impose directional steering on the merged circulation. And the very nature of a Fujiwara merger, as Fujiwara himself observed in his water tank, is that it is self-reinforcing. The merged circulation blocks the very jet stream configuration that would push it northeast. It doesn't leave. It sits, and it keeps raining. To understand what "it sits and keeps raining" means for the central United States, you need to understand what makes this particular piece of geography uniquely vulnerable to a stalled weather system. The Great Plains and the Midwest sit in a geography that is almost perfectly designed to amplify the damage from a slow-moving storm system. The terrain is flat. There are no significant mountain ranges to deflect or disrupt a merged circulation. The Rocky Mountains are to the west, and they play a role in cyclogenesis, in helping create the low-pressure systems in the first place, as cold air descends the lee slopes and forces surface divergence. But once a low is established on the plains, there is nothing to break it apart. The terrain offers no forcing. The flatness matters for another reason. Surface water on the Great Plains doesn't drain quickly. It pools. It fills the shallow depressions and the creek beds and the tributary channels. And those tributary channels feed rivers that are already carrying the runoff from the previous day's rainfall, which is feeding rivers that are carrying last week's rainfall. On the flat plains, hydraulic pressure doesn't dissipate. It compounds. And then there's the moisture supply. The central U.S. sits at the receiving end of what meteorologists call the low-level jet, a quarter of strong southerly winds at approximately 1,500 meters above the surface that transports warm, moist air from the Gulf of Mexico directly into the Central Plains. When a low-pressure system parks over Kansas or Nebraska, it draws that low-level jet directly into its circulation. The Gulf moisture doesn't stop arriving. It keeps coming. The storm doesn't exhaust its fuel source the way a tropical system over cooling water does. It is continuously resupplied. We know exactly what this combination, stalled atmospheric pattern, flat terrain, uninterrupted Gulf moisture, does to the Midwest because we've watched it happen before. In the summer of 1993, an abnormally stationary jet stream positioned itself over the central part of the nation. Kenneth D. King, Chief of Hydrologic Services at the NOAA National Weather Service Central Region headquarters in Kansas City, described it this way: "I think everyone was ready for some short-term heavy rain and serious flooding, but nobody thought it would last all summer." It lasted all summer. From May through September of 1993, major and record flooding occurred across North Dakota, South Dakota, Nebraska, Kansas, Minnesota, Iowa, Missouri, Wisconsin, and Illinois. Approximately 600 river forecast points across the Midwestern United States were above flood stage simultaneously. Not 600 gauges in one river system. 600 individual gauges across nearly 150 major rivers and tributaries. All of them, at once. Up to 38.4 inches of rain fell in east-central Iowa across the event. Rain measured in feet, not inches, because the storm pattern simply did not move. The Missouri River crested at 48.9 feet, at Kansas City on July 27th, breaking the previous record set in 1951 by 2.7 feet. Then the Missouri River crested, met the Mississippi River near St. Louis, and the Mississippi, which had already been near its own record stage, was pushed to a record crest of 49.47 feet at St. Louis on August 1st. 50 deaths, $15 billion in damage. The 1993 and 1994 harvests both lost. 10 commercial airports flooded. All railroad traffic in the Midwest halted. And that event, the most costly and devastating inland flood in American history, characterized by Lee Larson, one of the country's most respected flood hydrologists, as the largest and most significant flood event ever to occur in the United States, was driven by a single stalled jet stream pattern, not by two storm systems locked in a Fujiwhara interaction that were mutually reinforcing each other's stall, not by two circulations merging into a single amplified vortex that actively blocked its own steering mechanism, a single stalled pattern. That's what produced 600 simultaneous flood gauges, a Fujiwara merged superstorm over the same terrain with the same moisture supply, carries the same capacity for duration, but adds the unpredictability of binary interaction to the stall. The models couldn't predict the 1993 event, lasting all summer, and that was a well-understood atmospheric pattern. Binary interaction is the part the models have explicitly documented failure modes for. But there's a dimension to this that the rainfall totals and the river crests don't fully capture, a dimension that's invisible in the satellite images and absent from the 7-day forecast. And it lives not in the atmosphere above the central plains, but in the ground beneath it. Here is something that doesn't make it into weather forecasting broadcasts very often, but that hydrologists will tell you is often the most important number in any extreme rainfall event. The soil moisture content going in, not the rainfall amount, not the storm track, not the wind speed, the soil moisture content before the first raindrop of the event falls. This is because soil is the first line of defense against surface flooding. When rain falls on dry or moderately moist soil, the ground absorbs it. Infiltration. The water moves through the soil matrix, recharges groundwater, and eventually makes its way slowly into streams and rivers. The rate at which that process happens, the infiltration rate, determines how much of any given rainfall event becomes direct runoff. When soil is already saturated, when every pore space in the soil matrix is already occupied by water, the infiltration rate drops to something approaching zero. A saturated soil can absorb no additional moisture. Every drop of rain that falls on it becomes immediate surface runoff. You've taken soil that was functioning as a sponge and turned it into a parking lot. Yuxin Wu, a research scientist at the Lawrence Berkeley National Laboratory, has studied what happens when saturated soil encounters cold temperatures. In wet soil, Wu explained, you have ice form between the soil particles. Ice between the soil particles means the pore spaces aren't just full, they're sealed. The ground becomes, in effect, impermeable. Rain falling on it runs off instantly, at a rate that overwhelms any drainage system designed for normal conditions. In March of 2019, when a record-breaking bomb cyclone developed over southern Colorado and tracked east across Kansas, it arrived over terrain that had been prepared for catastrophe by months of conditions that the forecasting system had little ability to directly communicate to the public. The research team that analyzed the event, Crystal J. Stiles of the High Plains Regional Climate Center at the University of Nebraska-Lincoln, along with David Pearson and Paul Feynman of the National Weather Service in Omaha, published their findings in the Bulletin of the American Meteorological Society in 2020. Their characterization of the pre-storm conditions was precise. Frost depths of 60 to 90 centimeters across eastern Nebraska, western Iowa, and southeastern South Dakota. Rivers already frozen, the water equivalent of the snowpack sitting at 30 to 100 millimeters of compressed snow, waiting to liquefy the moment temperatures rose. When the cyclone's rain fell on this terrain, it didn't infiltrate. It couldn't. It ran off immediately, instantly converting inches of rainfall into inches of river rise, simultaneously across the entire basin. What followed was documented in numbers that still don't feel real when you read them. The Spencer Dam on the Niobrara River in Nebraska, a concrete structure that had stood since 1902, collapsed on March 14th. It released an 11-foot wall of water downstream, destroying 3 bridges in its path, one of them carrying a state highway. At Fremont, Nebraska, the Platte River breached a levee near the town of Fujiwara. The floodwater moved fast enough that the National Weather Service office in Omaha, the facility responsible for warning everyone else in the region, had approximately 1 hour to secure its equipment, implement continuity of operations procedures, and evacuate. The NWS staff loaded out and watched their own building go underwater. Nearly 50 levees breached along the Platte, Elkhorn, and Missouri rivers. 17 levees were breached or overtopped along the Missouri River alone across Iowa, Nebraska, and Missouri. In Fremont County, Iowa, the Missouri River crested almost 2 feet above the previous record, which had been set in 2011, itself a catastrophic event. In neighboring Mills County, the river reached 4 feet above the previous record. 3,300 miles of roads closed in Nebraska at peak. 27 state highway bridges washed away. I-29 in Iowa, a major interstate corridor, closed for several weeks. Researchers who documented the event described it as one of the longest times an interstate has been closed due to weather in U.S. history. The Pine Ridge Indian Reservation in South Dakota was isolated when floodwaters washed away its access roads. Residents were stranded for over 2 weeks. The final damage estimate for Nebraska alone, $1.9 billion. The costliest natural disaster in the state's history. Iowa reached $1.6 billion, also a state record. The governor of Iowa, Kim Reynolds, declared disaster in 67 counties. 67 counties. In a state with 99 counties total, that's more than 2/3 of the state under disaster declaration from a single weather event. And the Stiles team noted something in their 2020 analysis that deserves to be read carefully. After the flood event in March, they wrote, the region was entering the following winter season still completely saturated, with river levels largely above normal and soil moisture levels at or near capacity. The ground never fully recovered from 2019. It went into the following winter already compromised. The Army Corps of Engineers Kansas City District, in a statement that received far less attention than it deserved, warned early in 2020 that many levees on the Missouri and Kansas rivers that were damaged during the 2019 floods remained vulnerable to high water. More than 20 additional repair projects were not yet ready to bid. They hadn't been fixed. The river was still running high. The soil was still saturated, and the window for a second event to arrive before the first one was fully recovered from was wide open. Now consider what the preconditions for a major event in the Missouri River Basin look like when a Fujiwara merged, stalled superstorm arrives over terrain that is carrying that level of antecedent soil moisture. The ground isn't a sponge, it's a sealed surface. Every inch of rain the merged storm produces is a direct deposit into the river system. And a stalled merged system doesn't produce 1 inch of rain. It produces 5, it produces 8, it produces whatever the low-level jet can deliver from the Gulf of Mexico into a stationary circulation over the course of 5 days, 6 days, 7 days. But here's what the rainfall totals, and the river crests still don't capture. When the storm is stalled, and the roads are closed, and the levees are failing, the question that matters most isn't how much rain is falling. It's whether anyone can get to the people the rain is trapping. And that question has an answer. It's just not the one most people expect. When a major storm event hits the central United States, a tornado outbreak, a bomb cyclone, a significant flood event, the primary mechanism for reaching people who are cut off is helicopter. Not because it's the preferred option, but because it's often the only one. Roads flood. Bridges wash out. Boats work in calm water, not in fast-moving currents, carrying debris from collapsed structures. When 3,300 miles of Nebraska roads closed in March of 2019, and when the Pine Ridge Indian Reservation became an island with washed-out access routes on every side, the aerial option was what emergency managers looked to first. But aerial rescue operations have a number, a specific documented operational threshold, and a Fujiwara merged stalled superstorm sits directly on top of that number and stays there. Most helicopter rescue operations, including EMS helicopters, National Guard helicopters, and civilian search and rescue operations, are operationally grounded when sustained winds exceed 30 to 35 knots. That's approximately 35 to 40 miles per hour. The Federal Aviation Administration's Helicopter Flying Handbook is explicit about why. Wind is one of the three major factors affecting helicopter performance, alongside air density and aircraft weight. In sustained high winds, a helicopter's ability to hover, which is the entire operational requirement for a rescue hoist, for lowering a rescuer into a flooded second-floor window, for extracting someone from a roof, becomes compromised. In turbulent, directionally variable wind environments, the risks compound further. 35 knots. That's below tropical storm force. It's below the threshold that generates the highest impact warnings. A stalled, merged extratropical cyclone over the Central Plains can sustain winds of this magnitude for the entirety of its presence, not as a gust, not during a squall line passage, but as the continuous background wind field of the merged circulation. The Flight Safety Foundation, in its formal analysis of weather impacts on helicopter operations, describes the dynamic this way. Air movement, wind and turbulence, air density, and degraded visibility are of critical concern for helicopter pilots. Even the airflow generated by the helicopters themselves can be problematic. And crucially, it identifies mechanical turbulence, generated when prevailing wind encounters obstacles, as an especially dangerous condition for low-level flying. A Fujiwara merged circulation doesn't produce clean, unidirectional wind. It produces the turbulent, variable flow field of two interacting vortices, precisely the environment that compounds the operational risk beyond what a simple wind speed number conveys. There's a timing problem layered on top of the wind problem. When flood events cut off communities, the sequence of isolation goes roads first, then bridges, then emergency vehicle access, and finally aerial access as winds rise with the storm's intensification. But in a stalled, merged system, intensification and stalling happen simultaneously. The wind doesn't peak and then drop as the storm tracks away. It peaks and stays. The rescue window, the gap between when road access closes and when aerial access becomes viable, may not open at all for the first several days of the event. We saw a partial version of this problem in 2019. The Pine Ridge Indian Reservation in South Dakota was isolated when floodwaters washed away its access roads. Residents were stranded for over 2 weeks. 2 weeks is the recovery period for a single bomb cyclone that tracked northeast and cleared the region in 36 hours. Extend that event into a 5 to 7 day stalled Fujiwara merger, and the isolation doesn't last 2 weeks. It lasts as long as the wind stays up, which is as long as the merger persists, which is as long as there is no external atmospheric forcing, strong enough to break the binary interaction. In the Parma-Melor interaction, the stall lasted approximately 36 hours in its first phase before Melor's approach reactivated the interaction and sent Parma back over Luzon a second time. 3 landfalls, 3 separate periods during which communities were actively being inundated while recovery from the previous landfall was still underway. 3 separate windows during which the roads were either still closed or had been cleared only long enough for residents to begin moving back. Imagine that sequence over the flat terrain of the Missouri River Basin, where there are no mountain valleys to isolate impact zones from each other, where the flooding isn't localized to one watershed but spreads across the entire basin simultaneously, where the communities being isolated aren't on an island in the Philippines, they're along the Platte River Valley in Nebraska, along the Missouri River bottoms in Iowa and Missouri, in the towns and counties that the Army Corps of Engineers has already publicly flagged as sitting behind levees that remain incompletely repaired from the last major event. That's the rescue window problem. It's not a question of whether helicopters can fly in bad weather. It's a question of whether the window during which they can fly aligns with the period during which people need them. In a standard storm event, the answer is usually yes. The storm peaks and then tracks away, and within 12 to 24 hours, the wind drops and the aerial assets can move in. In a Fujiwara merge stalled event, the window and the need are precisely inverted. The need is highest exactly when the wind is highest, and the wind doesn't drop because the storm doesn't move. Now, a stalled superstorm with a closed rescue window is terrifying because of what it does to the people in its path. But to fully understand the mechanism of destruction, the specific physics of why a multi-day rainfall event over saturated plains terrain produces the damage it does, you have to go underground. You have to understand what happens when the soil, which is supposed to be absorbing some fraction of that rainfall and slowing its delivery to the rivers, stops functioning entirely. There is a specific moment in every major Midwest flooding event where the physics changes. It's not a dramatic moment. There's no sound, no visible change, nothing on a radar screen that marks it. It's the moment when soil moisture reaches field capacity, when the last pore space in the soil matrix fills with water and the ground's ability to absorb any additional rainfall drops to essentially zero. After that moment, the rainfall to runoff ratio is no longer a fraction. It becomes 1-to-1. Everything that falls runs off. Immediately, directly, into the creek, into the tributary, into the river. The ground that would normally slow and buffer the delivery of water to the river system has become, in the precise description of the Lawrence Berkeley National Laboratory researcher Yuxin Wu, something closer to a sealed surface. When water-saturated soil encounters freezing temperatures, ice forms between the soil particles, physically locking the pore spaces shut. But even without freezing, a fully saturated soil has reached the end of its buffering capacity. It is a parking lot. Rain falls on it and runs. In 1993, the soil across the upper Mississippi River Basin was already saturated going into the summer rainfall season. This was the consequence of a wet autumn in 1992, followed by above-average snowfall during the winter, followed by spring snowmelt that left the ground at or near field capacity before the first summer thunderstorm arrived. Kenneth King, Chief of Hydrologic Services at the NOAA National Weather Service Central Region Headquarters in Kansas City, described the preconditions with what in retrospect sounds like understatement. The stage was set in 1992 with a wet fall, which resulted in above-normal soil moisture and reservoir levels in the Missouri and upper Mississippi River basins. When the rainfall began in June of 1993 and didn't stop, when the jet stream locked itself over the central part of the nation and began steering storms into the same basin week after week, the runoff was essentially instantaneous. Rainfall amounts of 5 to 7 inches in 24 hours were documented as common during July. 5 to 7 inches across a watershed, where every inch runs off immediately, is not the same as 5 to 7 inches on a watershed that can absorb 2 or 3 of those inches and slow the delivery of the rest. It is an immediate, undiluted deposit into the river system. The result was the Missouri River cresting at 48.9 feet at Kansas City on July 27, 1993. That crest didn't build slowly. It built at the speed of runoff across a saturated basin, faster than the river gauges upstream could warn the gauges downstream in some cases, faster than the models had projected because the model's soil moisture component was operating on a pre-event estimate that the actual saturation conditions had long since exceeded. The soil moisture model in primary operational use during the 1993 event was the Antecedent Precipitation Index, or API model. The Army Corps of Engineers later documented this as one of the primary constraints on flood forecast accuracy during the event, not because the model was poorly designed, but because the antecedent conditions it was working from had been rendered irrelevant by a saturation state that the model hadn't been designed to represent. Now extend this physics to a Fujiwara merged stalled system. A standard bomb cyclone event, the March 2019 event, produced record rainfall in the range of 1 to 3 inches across a broad area, with locally higher totals, over a period of approximately 36 hours. That event, falling on frozen saturated soils, produced the Spencer Dam collapse, nearly 50 levee breaches, and $1.9 billion in Nebraska damage. $1.9 billion. From 36 hours of precipitation on pre-saturated ground. A stalled Fujiwara merged superstorm over the same terrain doesn't produce 1 to 3 inches in 36 hours. It produces 1 to 3 inches per day, sustained over 5 to 7 days. The Parma-Melor interaction resulted in Typhoon Parma surviving approximately 14 days. Approximately 5 of those days spent over the island of Luzon, continuously producing rainfall that had nowhere to go on terrain where the rivers had already crested from the first landfall. In the American Midwest analogy, day 1 of the merged storm event, the rivers are rising. Day 2, they are above flood stage. Day 3, the first levee sections are reaching their design limits. Day 4, with the ground having rejected every drop of rainfall as direct runoff since early on day 1, the rivers are in territory that the levee system was never designed to handle. Day 5, the merged circulation is still sitting over Kansas and Nebraska, the low-level jet is still pumping Gulf moisture into it, and the radar is still showing heavy precipitation bands rotating around a stationary center. And something else is happening by day 5 that didn't matter much on day 1. The rivers upstream are cresting, and their crests are traveling downstream toward communities that were barely holding on, toward levee sections that were already at their limits. In a single event flood, the upstream crest travels downriver on a known timeline. Forecasters can track it, project when it will arrive, issue warnings in advance. In a stalled merged event, there is no single upstream crest. There are multiple crests from multiple tributaries, all arriving at the main stem within days of each other, because all of them have been receiving continuous rainfall simultaneously. The Army Corps of Engineers has a term for this: compound peak flow. It's when the main stem river can't distinguish between the natural upstream crest arriving at its normal pace and the new rainfall arriving directly from the still active storm. The two events overlap. The river has no recovery period between them. That's what makes the physics of a Fujiwhara merged stalled system categorically different from a single extreme event. And it's what makes the infrastructure underneath the merged storm the most critical variable in understanding just how bad the worst-case outcome actually is. And this is where the story takes a turn that most coverage of the Fujiwara effect completely misses. The question of what a stalled superstorm does to the Midwest isn't primarily a meteorological question. It's an engineering question. Specifically, it's a question about whether the levee system along the Missouri and Platte rivers, a system that was significantly damaged in 2019, partially repaired since, and publicly flagged by the Army Corps of Engineers as containing multiple remaining vulnerabilities, can survive 5 to 7 days of compound peak flow from a stalled Fujiwara merger. The Army Corps of Engineers Kansas City District manages levee systems across western Missouri, northeastern Kansas, southern Nebraska, and southwestern Iowa. In early 2020, the Corps issued a warning that received far less attention than its implications warranted. Many levees on the Missouri and Kansas rivers that had been damaged during the devastating 2019 floods remained vulnerable to high water. Projects at 13 sites were preparing to begin work. More than 20 additional projects were not yet ready to bid. The Corps described challenging weather conditions and higher flows that had persisted through the winter, continuing to delay full assessment of damaged levee systems. Read that again. Not repaired, not fully assessed, flagged as vulnerable. And that was before a Fujiwara merger loaded the upstream watershed with 5 to 7 days of continuous heavy precipitation. Here is how levee failure cascades. A levee section in Holt County, Missouri, overtopped by a rising river, doesn't just flood Holt County. The water that breaks through the breach accelerates downstream. It adds hydraulic load to the next levee section south. If that section is already near its design limit, if it was already carrying water within a foot or two of its crest, which is exactly the condition documented in multiple Missouri river gauges during the 2019 event. The additional water pushed by the upstream breach can be the difference between holding and failing. During the 2019 event alone, 17 levees were breached or overtopped along the Missouri River across Iowa, Nebraska, and Missouri. In Fremont County, Iowa, the Missouri River crested almost 2 feet above the previous record, a record that had been set during the 2011 flooding. In neighboring Mills County, river levels reached 4 feet above the previous record. In Holt County, Missouri, 30,000 acres of the county's 95,000 total acres were flooded. That water didn't fully recede until late October, more than 7 months after the initial event. 7 months. From a single bomb cyclone that tracked northeast and cleared the region in under 2 days. The 1993 Great Flood provides the clearest documentation of what compound peak flow does to a basin-wide levee network. The Army Corps' own historical assessment describes the moment when both the Mississippi and Missouri rivers approached their crests simultaneously near St. Louis. The two rivers converging at their confluence within days of each other, each one already pushing record flow levels, neither one giving the other any room to absorb the additional hydraulic load. The Missouri River stalled at near record stages for days, seemingly waiting for the Mississippi to arrive at its own crest. Then both rivers hit their peaks at roughly the same time. The result was a confluence event that overwhelmed levee sections designed to handle one river cresting at a time, not both. Bridges on the Mississippi were out from Davenport, Iowa to St. Louis, Missouri. On the Missouri River, bridges were out from Kansas City downstream to St. Charles, Missouri. Barge traffic on both rivers stopped for nearly 2 months, not for days, for months. And some locations on the Mississippi remained in continuous flood for 6 months after the event began. Now add to that picture the specific condition that a Fujiwhara merged or stalled system creates that the 1993 event didn't have. The source of the precipitation is not moving. In 1993, individual storm systems moved through the region repeatedly across a multi-month period, each one adding to the accumulated soil moisture and river levels. There were breaks between them, brief, insufficient breaks. The ground never fully recovered, but breaks. The river gauges had occasional periods where they weren't actively rising. In a stalled Fujiwara merger, there are no breaks. The precipitation is continuous. The river gauges don't plateau. They climb. For as long as the merger persists, for as long as the low-level jet supplies Gulf moisture into the stationary circulation, for as long as the merged system holds together against any steering flow, the rivers rise. And when the levees fail, they don't all fail at once. They fail in sequence, each upstream failure adding hydraulic load to the next downstream section, which adds hydraulic load to the section after that, which is the Cascade scenario that makes a distributed levee network fundamentally different from a single large dam. A dam, when it fails all at once. A levee network, when it fails progressively, each breach taking time, each one shifting the failure point downstream, giving communities a few hours of warning, or in some cases, a few minutes. That's the levee calculus. It's not whether the levees will hold under a 5-day stalled merged superstorm. Given the documented vulnerability state of the Missouri River Basin levee system, as of the most recent Army Corps assessment, the question is which sections fail first, in what sequence, and whether the communities downstream have enough warning time to act before the Cascade reaches them. The 1993 Great Flood produced numbers that still serve as the benchmark for catastrophic inland flooding in the American experience. 50 deaths, $15 billion in damage across 9 states, equivalent to roughly $30 billion today. Approximately 320,000 square miles of the Mississippi and Missouri River basins affected, an area larger than Texas and California combined. Transportation didn't just suffer, it ceased. Barge traffic on the Missouri and Mississippi rivers stopped for nearly 2 months. Bridges on the Mississippi were inaccessible from Davenport, Iowa to St. Louis. Bridges on the Missouri were out from Kansas City downstream to St. Charles. 10 commercial airports were flooded. All railroad traffic in the Midwest halted. Not rerouted, not delayed. Halted. The supply chain for the entire agricultural interior of the United States stopped moving waterbound freight for nearly 60 days. Sewage treatment and water treatment plants were destroyed, not damaged, destroyed. Communities along the affected rivers lost access to treated drinking water. The 1993 and 1994 harvests were both lost, not because the crops couldn't be planted, but because the land was underwater. When planting time came, and still recovering in many cases when harvest time arrived. That's what Cascade looks like. Not one failure, not a collection of simultaneous failures. A progressive, interlocking sequence of failures, each one expanding the zone of impact, each one removing another layer of infrastructure that the recovery process depends on, until the response system is not just strained, but dismantled. Until the National Guard helicopters are grounded by wind, the roads are underwater, the bridges are out, the railroads aren't running, the water treatment plants are compromised, and the only functional communication link between affected communities and the outside world is a satellite phone in a county emergency manager's office, if the county emergency manager can get to the office. To understand what a compounded version of this, not just a single prolonged stalled pattern, but a Fujiwara merged circulation actively reinforcing its own stall, could produce in the 21st century Midwest, it helps to look at what happened the last time Western Europe experienced something structurally similar, not a Fujiwara merger, not two systems locked in binary interaction over land, but two violent extratropical cyclones striking the same infrastructure along the same corridor 24 hours apart, each one finding the damage from the previous still fresh, the power still out, the emergency services still overwhelmed, the roads still impassable. December the 25th and 26th, 1999. Cyclone Lothar formed over the North Atlantic on Christmas Day and crossed France in approximately 9 hours. From the Brittany coast in the early morning to the German border by midday. Gusts of up to 210 kilometers per hour were recorded at the Palace of Versailles. Average sustained winds at the Orly weather station outside Paris reached 115 kilometers per hour, the equivalent of a strong Category 1 hurricane. Cyclone Lothar's forecast was, by the admission of the meteorological community afterward, catastrophically poor. The European Center for Medium-Range Weather Forecasts had correctly predicted the jet stream configuration 9 days before Lothar struck France. The large-scale pattern was foreseeable, but the intensity of Lothar itself, at the level of detail relevant to warning the public and positioning emergency resources, was not well predicted. Météo France issued a warning of a strong storm with the correct path approximately 24 hours before landfall, but the warning underestimated the wind speeds. 2 hours before Lothar hit Paris, the forecast was still materially wrong. One meteorologist later described the available forecasts as split between those that were poor and those that were very poor. Lothar killed 110 people. It caused more than 15 billion euros in damage, the costliest European windstorm ever recorded at the time. The day after Lothar, Cyclone Martin followed along the same track. Another violent extratropical cyclone. The same corridor, winds approaching 200 kilometers per hour in the Charente-Maritime region of France. Another 30 deaths, another 6 billion euros in damage. Combined, Lothar and Martin killed 140 people across Western and Central Europe. 9.9 billion euros in combined economic losses. 3.4 million customers in France without electricity, a number that forced EDF, the French national electricity utility, to acquire every available portable power generator in Europe. Some were brought from Canada. The two storms together destroyed 200 million cubic meters of forest, the equivalent, Swiss Re later calculated, of an uninterrupted train convoy of timber running from Oslo to Gibraltar. 1/4 of France's high-voltage transmission lines were brought down, 300 high-voltage poles broken. It was, Swiss Re characterized it, one of the biggest power outages ever experienced by a modern developed country. And critically, this is the point that connects Lothar and Martin to the Fujiwara scenario over the American Midwest. Lothar's forecast failure was later attributed by meteorological researchers to the same mechanism that breaks model skill during binary interaction. An unusually strong and straight jet stream, high atmospheric instability, a situation that made precise intensity prediction extremely difficult, even when the large-scale pattern was correctly anticipated. Lothar and Martin were not a Fujiwhara merger. They were sequential events on the same jet stream, not locked, co-equal systems mutually reinforcing each other's stall. But they demonstrate with brutal clarity what happens when infrastructure designed for individual extreme events encounters compound extreme events, events that arrive before the recovery from the previous one has begun. Lothar killed 110 people and caused 15 billion euros in damage. Martin killed 30 more the next day. The infrastructure that survived Lothar didn't survive Martin, not because Martin was necessarily stronger, but because Lothar had already broken it. American Midwest infrastructure hasn't been designed for a single storm that simply doesn't leave. And the levee system along the Missouri River Basin, flagged, damaged, partially unrepaired, is the specific named infrastructure that a stalled Fujiwara merger will reach first. The storm that doesn't leave. That's what the forecasters are looking at. That's why they're using the word terrified. And to understand why the forecasting failure is not a failure of effort or of intelligence. Why it is a fundamental limitation built into the operational science at the exact point where it matters most. You need to go inside the models themselves. The National Oceanic and Atmospheric Administration's global forecast system runs 4 times every day. It ingests observational data from radio sondes, the instrument packages carried aloft by weather balloons, from weather satellites, from ground-based stations, from ocean buoys, from aircraft, from radar networks. It processes that data through a set of mathematical equations describing the physical behavior of the atmosphere, and it produces a forecast for single system events, a single low-pressure center tracking across the continent, a cold front sweeping southeast, a developing supercell over the Oklahoma Panhandle. The GFS is extraordinarily capable. Forecasts of large-scale atmospheric patterns are now routinely skillful out to approximately 2 weeks. The broad strokes of what the weather will look like 10 days from now are often remarkably accurate. This is one of the genuine achievements of 20th century science, and it saves lives every time it allows emergency managers to pre-position resources before a major event. But the National Weather Service's own documentation is candid about what the GFS and every other operational NWP model shares as a structural limitation. Almost every step in numerical weather prediction, the NWS states in its own published materials, includes omissions, estimations, approximations, and compromises. The model doesn't solve the atmosphere. It approximates it with mathematical shortcuts called parameterization, schemes that substitute simplified representations for physical processes too complex to compute directly at the model's spatial resolution. Those approximations work remarkably well for individual storm systems. They fail in a documented, repeatable, and structurally understood way when 2 storm systems begin to interact. Here is why. A forecast model works by evolving the current state of the atmosphere forward in time. The current state, the initial conditions, is constructed from the observational data the model has ingested. Small errors in those initial conditions are normal. They are unavoidable. The observational network, as dense as it is, cannot measure every parcel of air, everywhere, all the time. There are gaps, there are interpolations, there are measurements with error bars. For a single storm system, those initial condition errors remain small relative to the size of the storm for the first several days of the forecast. The storm is large enough that the error is a small fraction of the total. But when 2 storm systems begin to interact, when Fujiwhara binary interaction commences and the outcome becomes sensitive to the precise ratio of size and strength between the 2 systems, those same small initial condition errors suddenly become enormous in their consequences. A 2% error in estimating the central pressure of System A relative to System B doesn't produce a 2% error in the forecast track. It produces the difference between a forecast that shows System A absorbing System B in a partial straining out scenario and a forecast that shows both systems merging into a stationary supersystem that parks over the Missouri River Basin for 6 days. That's not a 2% difference in outcome. That's the difference between a managed flood event and a regional catastrophe. A research team studying large track forecast errors in the western North Pacific analyzed 44 typhoon cases with track errors exceeding the 75th percentile of the annual error distribution, the worst quarter of all forecast busts documented in the TIG dataset between 2007 and 2014. They identified 4 categories of situation associated with these large errors. One of those 4 categories was, specifically, the interaction of a cyclone's outer structure with other tropical weather systems, not the most unusual circumstance in typhoon forecasting. One of 4 categories, present in a meaningful fraction of the worst forecast failures in the dataset. Cyclone Lothar, to return to the European precedent, illustrated this dynamic with particular clarity. The European Center for Medium-Range Weather Forecasts correctly predicted the jet stream configuration 9 days before Lothar struck France. The large-scale pattern was well forecast, but the intensity and precise timing of Lothar's landfall, the information actually relevant to whether Parisians should be boarding up their windows, was still materially wrong 2 hours before the storm arrived. The forecasters knew something bad was coming. They could not tell you how bad, or exactly where, or exactly when, at the resolution of detail that emergency preparedness requires. The Parma-Melor research team's finding is even more direct. Their paper, published in 2020, examined Typhoon Parma's track using the Liu empirical formulas specifically developed for analyzing Fujiwara interactions. Their conclusion was that the track, 3 landfalls, multiple course reversals, a stall over the South China Sea, a return over Luzon, was extremely difficult, if not impossible, to forecast using the numerical weather prediction models available during the event. 500 people died from a storm that the models believed was already dying. Now here's the critical question for the operational meteorologist working the desk at the National Weather Service office, responsible for Missouri and Iowa right now. They know a Fujiwara interaction may be developing. They can see the ensemble spread, the range of possible solutions across multiple model runs, widening as the 2 systems close the distance between them. They know, from the research literature, that the outcome is highly sensitive to the size and strength ratio of the 2 systems at the moment of closest approach. They know that ratio cannot be measured with sufficient precision to constrain the model's diverging solutions. What do they tell the public? The NWS is guided by a protocol of probability and timing. It issues forecasts and warnings based on what the majority of ensemble members indicate, weighted by model skill. When the ensemble spread is narrow, that communication is confident and clear. When the ensemble spread is wide, when the models are producing dramatically different solutions with roughly equal probability weights, the communication becomes necessarily hedged. A significant weather event is possible. Elevated flood risk through the weekend, monitor conditions, and be prepared to act quickly. That language is honest. It accurately represents what the science knows and doesn't know, but it does not communicate to the family in Holt County, Missouri, with a recently repaired first floor and a basement still showing the waterline from 2019. It does not communicate the specific possibility that the storm currently being tracked as a standard rain event could, depending on which side of the forecasting envelope materializes, stall over their watershed for 6 days, put the river 4 feet above the previous record, and cut off the roads before the rescue helicopters can fly. The gap between what the operational science knows and what it can communicate at the level of resolution that individual households and emergency managers need, that gap is the specific vulnerability that a Fujiwara interaction exploits. And it is the reason that the decisions made in the next 48 to 72 hours by emergency managers working from imperfect model guidance will determine whether the communities in the merger's path have enough warning to act before the cascade begins. Put yourself in the position of the emergency manager for a county along the Missouri River in western Iowa. You have received a briefing from your regional NWS office. There is a significant weather system, potentially two interacting systems developing to your west and southwest. The forecast shows elevated flood risk. The ensemble models are divergent. The high-end scenario involves rainfall totals that would challenge the levee system. The low-end scenario is a manageable event. You have a budget, you have pre-positioned resources that cost money to activate. You have a county that is still showing damage from the 2019 event. Roads not fully repaired, some levee sections still awaiting full inspection. You have residents who have been through years of elevated flood risk, who are experiencing forecast fatigue, who have been told to monitor conditions and be prepared to act quickly, enough times that the phrase has stopped carrying the urgency it was designed to convey. And you have a forecast that, because of the binary interaction dynamics of what may be a Fujiwara merger in progress, has an honest uncertainty envelope that spans the distance between significant but manageable and generational catastrophe. What do? This is not a hypothetical. This is the documented operational reality of emergency management when confronted with compound extreme events. The closer historical analog in terms of this decision structure is Hurricane Harvey, which made landfall near Rockport, Texas in late August of 2017 as a Category 4 hurricane with 130 miles per hour sustained winds. Harvey is relevant here not because of its wind speed. The Fujiwara scenario is not a tropical system, but because of what Harvey did after landfall. It slowed, then it stalled. Harvey sat over southeast Texas and produced approximately 60 inches of rain in approximately 4 days. Not 4 days of moderate rainfall that totaled 60 inches. 4 days of continuous, catastrophic rainfall that overwhelmed every drainage system, every retention basin, every levee, every pumping station in the Houston metropolitan area. 68 people died directly. Total damages reached approximately $125 billion, making Harvey the costliest disaster in American history at the time. Harvey's stall was tropical in origin. It was cut off from its steering flow when the subtropical high ridges on either side of it collapsed. It's a different mechanism from the Fujiwara stall, but the consequence of the stall is structurally identical. A storm that should have moved didn't, and every additional hour it sat, the rainfall to damage conversion rate climbed because the ground was increasingly saturated, the drainage systems were increasingly overwhelmed, and the rescue capacity was increasingly strained. The emergency managers in Harris County, Texas, in August of 2017 were working from forecasts that captured Harvey's intensity but underestimated both the stall duration and the rainfall totals. The model showed a storm that would stall briefly and then begin moving. It didn't move. It kept raining. The decisions that had been made based on the model's predicted track and duration were made with good information. The model's information was wrong. Now consider the Missouri River Valley emergency manager making resource decisions in the window before a potential Fujiwara merger resolves into one outcome or another. The NWS can tell them there's elevated flood risk. It cannot tell them with operational useful confidence whether this becomes Harvey or whether it becomes a manageable 2-day rain event. The binary interaction mechanics that govern that distinction are exactly the mechanics that operational NWP cannot reliably model. The Pine Ridge Indian Reservation isolation in 2019 lasted over 2 weeks, from a single bomb cyclone that cleared the region in under 48 hours. A Fujiwhara merged stalled event over the same terrain doesn't produce 2 weeks of isolation. It produces isolation for the duration of the event plus the recovery period. The duration of the event, under the worst-case interpretation currently consistent with the evidence, is measured not in days, but in the time it takes for external atmospheric forcing to break the binary interaction, which is, by definition, unpredictable. In Iowa alone, the 2019 event resulted in Governor Kim Reynolds declaring disaster in 67 of the state's 99 counties, more than 2/3 of the state. In Nebraska, Governor Pete Ricketts estimated damage exceeding $1.9 billion. These were single event outcomes from a storm system that did not stall. The March 2019 bomb cyclone tracked northeast and cleared the region. The flooding lasted months, but the rainfall event itself lasted days. Multiply the rainfall duration by 5. Multiply the soil saturation at the event onset by the documented persistent saturation the Stiles research team found lingering into the 2019 to 20 winter season. Layer on the documented unrepaired levee vulnerabilities. Close the rescue window with sustained winds in the 35 to 40 mile per hour range for the duration of the event. That's what the emergency manager is trying to make decisions in advance of, with imperfect model guidance, with a public experiencing forecast fatigue, with a levee system that the Army Corps has publicly stated is not fully repaired. And what makes this moment genuinely distinctive is not the severity of any one of those factors in isolation. It's the simultaneous presence of all of them. The soil saturation, the levee vulnerabilities, the rescue window, constraints, the model failure mode. Individually, each one is a manageable risk. Together, under a Fujiwara merged stalled superstorm, they are a compound system failure. The analogy is not one thing breaking. It's the sequence of breaking. Roads first, then levees, then rescue access, then communication, then water treatment, then food supply chain, each failure removing one more layer of resilience from the communities in the merged storm's footprint, until the last layer fails, and there is nothing left to absorb the next failure behind it. Duration is not just a multiplier on damage. Duration is the mechanism by which compound failures become total failures. And duration is exactly what a stalled Fujiwara merger produces. The number that most fundamentally distinguishes a Fujiwara merged, stalled superstorm from every other extreme weather event in the central U.S. record is not the wind speed or the rainfall total per hour. It's the rainfall total across the full event duration. And the duration is the variable that no standard weather communication framework is designed to convey. The 1993 Great Flood is the benchmark for what duration does to a basin. But even in 1993, the rainfall wasn't truly continuous. It came in episodes, storm systems moving through on a recurring jet stream pattern, each one depositing additional moisture on a basin that hadn't recovered from the last. There were gaps between the individual events, even if those gaps were too short for the rivers to fall below flood stage. The prolonged nature of the 1993 flooding was the result of a recurring pattern, not a single persistent system. After the initial March 2019 bomb cyclone event, the National Weather Service documented something that captures the duration problem precisely. Rain fell somewhere in the Missouri River Basin every single day from March 14th through July 29th of 2019. 137 consecutive days with precipitation somewhere in the basin. Not 137 days of extreme flooding, but 137 days of accumulated moisture on a watershed that started the sequence already saturated and never had a chance to dry out between events. The agricultural impact of that duration is documented in numbers that are almost difficult to process. The 2019 floods caused $440 million in crop losses in Nebraska alone, $400 million in cattle losses, in the state that is the fourth largest cattle producer in the United States. The nutrient-rich topsoil that had been building in Nebraska's river bottoms for decades was washed away and deposited in the Missouri and Mississippi rivers. Farmers who had operated those bottomland fields for generations were told by agronomists that rebuilding soil productivity to pre-flood levels would take years. Some sections of bottomland farmland near the Missouri River in Nebraska were still underwater in November of 2019, 8 months after the initial event. Typhoon Parma's Fujiwara interaction with Melor resulted in approximately 14 days of total storm lifespan, with approximately 5 of those days spent continuously impacting the Luzon watershed. 5 days of continuous rainfall over the same watershed. Not 5 days of episodic storms. 5 days of a persistent circulation producing rainfall over terrain that had already experienced the first landfall and was receiving the second and third. The Science Direct research paper on the Parma-Melor interaction characterized the cumulative impact in specific terms: a big flood over a large area with nearly 500 fatalities. economic losses of $581 million from a storm that had already weakened to tropical storm strength before the Fujiwhara interaction reactivated its impact. Now consider what 5 continuous days of heavy precipitation from a Fujiwhara-merged superstorm means for the Missouri River Basin precipitation trend. The National Centers for Environmental Information documented in their 2019 Extreme Wetness Report that basin-wide precipitation has increased by approximately 8% since 1895. Spring precipitation, the season when extratropical Fujiwara interactions are most likely in this region, is up 14%. Autumn precipitation is up 14%. These are not projections. These are measurements. The basin is wetter, statistically, than it has ever been in the instrumental record. Climate Signals, in their analysis of the March 2019 bomb cyclone, noted that modeling studies consistently suggest that the frequency and intensity of severe storms in the United States could increase as climate changes, particularly over the U.S. Midwest and southern Great Plains during spring. Not particular storms, not specific events, the statistical frequency of the conditions that produce them. What this means for the Fujiwara scenario is not primarily about attribution, about whether climate change caused this specific interaction. It means that the preconditions that determine how catastrophic any given stalled weather system becomes, soil, moisture levels, river baseline flows, levee stress states, are systematically more unfavorable than they were a century ago. The same storm over the same basin does more damage today than it would have done in 1921, not because the storm itself is necessarily more intense, but because the basin it's landing on is carrying more water to begin with. Duration is the weapon, and the weapon is landing on a landscape that has been progressively more saturated statistically for the past century. There is one more thing this investigation needs to address before we get to the assessment, because whenever a topic involves extreme weather events, institutional communication gaps, and the kind of forecast uncertainty we've been describing, whenever the science is genuinely alarming and the models are genuinely limited, a specific category of claim begins to circulate. And some of those claims are not just wrong. They are wrong in a way that specifically prevents people from understanding and responding to the actual threat. I want to address something directly because it deserves an honest answer grounded in physics rather than dismissal. Whenever an extreme weather event develops in the central United States, particularly a large, anomalous, poorly predicted event, a set of claims begins circulating on social media and in certain online communities. The claims typically center on weather manipulation, that the storm was created, steered, or amplified by human intervention using technologies like HAARP, the High Frequency Active Auroral Research Program, operated by the University of Alaska Fairbanks, or by large-scale cloud seeding programs, or by some combination of classified government technology. The impulse behind these claims is, in a certain sense, rational. When events are this extreme, this poorly predicted by the systems we rely on, this catastrophic in their human consequences, people look for explanations. The official narrative is, the atmosphere is complicated. That feels insufficient when you're watching your home flood for the third time in a decade. It feels like a non-answer. But the specific explanations being offered fail on physics, not on politics, not on trust of institutions, on the basic arithmetic of energy. HAARP operates at a maximum power output of approximately 3.6 megawatts. That is a significant engineering achievement. It is also, when measured against the energy budget of a mid-latitude cyclone, completely irrelevant. A single mature extratropical cyclone releases energy at a rate measured in petajoules per day. 1 petajoule is 10 to the 15th power joules, 1,000 trillion joules. The energy released by a large mid-latitude cyclone in a single day exceeds HAARP's total power output by approximately 12 orders of magnitude. 12. That's not a rounding error. That's the difference between a flashlight and the sun. You cannot steer a hurricane with a flashlight. The energy isn't there. Cloud seeding is a real technology with real, documented effects. Silver, iodide particles introduced into supercooled cloud cover can enhance precipitation by approximately 5 to 15% under specific, favorable conditions. This technology has been used for agricultural purposes for decades. It is not a secret. It is also not capable of creating a storm system from clear air, and it operates on spatial and temporal scales orders of magnitude smaller than a Fujiwara interaction between two mature extratropical cyclones, spanning hundreds of thousands of square miles. The specific mechanism, binary cyclone interaction, that we've been investigating for this entire episode was described by a Japanese scientist doing water tank experiments in 1921. It is a fundamental property of rotating fluid dynamics. It operates under the same physics whether HARP exists or not, whether cloud seeding programs exist or not, whether any government agency wishes it to occur or not. Two vortices of equal strength in proximity in a rotating fluid will orbit each other and merge. That's not a government program. That's Fujiwara's water tank. Here is what the real human fingerprint looks like in this story. Not a directed energy weapon, not a classified weather control program. It's the documented 8% increase in Missouri River Basin precipitation since 1895, driven measurably by a warming atmosphere that holds approximately 7% more water vapor per degree Celsius of temperature increase, a relationship called the Clausius-Clapeyron equation, established by 19th century thermodynamics and confirmed by a century of atmospheric measurement. It's the 14% increase in spring precipitation specifically, the season when Fujiwara interactions over the Central Plains are most likely. It's the documented trend toward more intense extreme precipitation events, not just more frequent mild ones. Those are measurable. They have named authors. They have published data sets. They are not opinion. And they are, on their own, alarming enough. The actual physics does not need embellishment. The Clausius-Clapeyron relation doesn't need a conspiracy to be concerning. An 8% increase in basin precipitation over a century doesn't need a secret government program to explain it. The science of why a Fujiwara-merged superstorm landing on a progressively wetter basin does progressively more damage is complete and coherent without any of the fringe material layered on top of it. The conspiracy explanation is wrong, and the actual explanation is alarming enough. The impulse to look for additional explanations is understandable. The physics that produces the risk is harder to be angry at than a named actor with a named program. But the risk is real, regardless of whether there is a named actor. The rivers are rising, the levees are documented as vulnerable. The models have a known failure mode at exactly this kind of interaction. And the next 48 to 72 hours will determine which of several possible outcomes this Fujiwara interaction produces. So let's talk about what those outcomes actually are.